Hello friends, welcome to this video by Gild Academy. Today, we are going to discuss one of the most sought after problem solving methodologies, and that is dynamic programming. But before we get into the definition of dynamic programming problems, let's try to understand some of the situations which we might fall into while solving a fairly complex programming problem. So at times when we are presented with a programming problem, we try to solve that problem by dividing the problem into subproblems, and then we continue to divide those subproblems into further subproblems till the time we get to a level where the subproblems can be solved fairly easily. Then we solve those subproblems and merge their solutions to find the solution of the parent subproblem at a higher level. We continue to merge the solutions of the subproblems till the time we get the solution of the actual problem that was provided to us. This kind of a problem solving technique is known as divide and conquer technique. But there is a very important observation to be made in this kind of a hierarchical representation of problem and subproblems when we use divide and conquer technique. And the observation is that the subproblems at a lower level have exactly one parent subproblem at the higher level. So all the subproblems at level 3 have exactly one parent subproblem at level 2, and all the subproblems at level 1 have exactly one parent subproblem, and that is the actual problem. But this might not be the case every time. We might fall into a situation where multiple problems at a lower level may have more than one parent subproblem at a higher level. We can also say that the subproblem at a higher level may have more than one common subproblems at the lower level. Let's try to have a closer look in order to understand this properly. So if we see the first subproblem at level 1, the hierarchical representation of the subproblems may look somewhat like this. And the second problem at level 1 can have a hierarchical representation of subproblems which might look somewhat like this. If we merge both these hierarchical representations, then we'll see that the highlighted subproblems are the ones which are common to both these subproblems at level 1. So these highlighted subproblems are the ones which get calculated when we are solving the first subproblem at level 1, and the same highlighted subproblems get computed again when we are solving the solving the second subproblem at level 1. As you might agree that this is not a very efficient way of solving the problem because we are solving the same problem again and again. A problem statement that has this kind of a property where the problems at a particular level may have more than one common subproblem at lower level is known as the situation of overlapping subproblem. So one of the main properties to look for in a particular problem to decide whether dynamic programming can be used to solve that problem or not is overlapping subproblem. Another property to look for is optimal substructure, but that is something we'll cover in a separate video. Let's try to understand the problem of overlapping subproblems, and to do that we'll try to take an example. The example that we are going to take is that of Fibonacci series. As you might be aware that a Fibonacci series is a series of numbers that begins with 1, and any number in the series is basically the sum of the previous two numbers in the series. So if we are asked to write a code for this, we can very easily write a very simple implementation of the Fibonacci series, which might look somewhat like this. But in order to write a recursive implementation of Fibonacci series, it's very important to understand the definition of nth value of a Fibonacci series. So the nth value of a Fibonacci series is basically 1 if n is less than or equal to 2. Otherwise, we need to see what the n minus 1 and n minus 2 values of Fibonacci series are, and we need to add them both. So we can have a very simple recursive implementation of Fibonacci procedure, which might look somewhat like this. Let's try to understand the hierarchical representation of the problem when we are trying to find the fifth value of the Fibonacci series. So when we are trying to find the fifth value of the Fibonacci series, we can see that we need to find the fourth and the third value of the Fibonacci series, and the fourth value of the Fibonacci series is basically going to be the sum of the third and the second value. In order to find the third value of the Fibonacci series, we need to know what the second and the first value are, and we need to add them both. In this kind of a hierarchical representation, you can clearly see that the third value of the Fibonacci series is being calculated twice. So in order to find the fifth value of the Fibonacci series, we need to find the Fibonacci, find the third value of the Fibonacci series twice, and we are finding the second value of the Fibonacci series thrice. Such numbers can go up when we are trying to find a higher number in the Fibonacci series. So this is because we have a problem of overlapping subproblem. We'll try to understand the extent of this particular problem, that is the problem of overlapping subproblems, in the efficiency of our recursive implementation for Fibonacci series. So let's try to do this, and let's try to understand the extent of inefficiency caused by the problem of overlapping subproblems by writing a simple Java code. So a very simple Java implementation to find the nth value of the Fibonacci series could be somewhat like this, where we'll have a method named as Fibonacci, and we'll pass n to that method, which will tell us the number of the Fibonacci series that we are trying to calculate. In order to have a better intuition of the inefficiency that is being caused by the problem of overlapping subproblems, we'll try to call this method again and again iteratively in order to find the first n numbers in the Fibonacci series. N is something that we will be setting as per our convenience. So let's have a quick implementation of this method, and let's try to see the extent of the inefficiency that can be caused. So as you can see that I have a recursive implementation of Fibonacci method, and I will be passing the n over here, and this n is actually getting passed iteratively from 1 to n, where I've set n to 100. For the sake of convenience, let's begin with the number 45. And once the main method is done with its execution, will print the amount of time that this particular method took. So let's quickly run this method and see. As we can clearly see that as the value of n increases, the amount of time to calculate the nth value of the Fibonacci series also increase. So in this case, it took approximately 9 seconds to calculate the first 45 numbers in a Fibonacci series. This is not a very good performance, but this is what we have when we are using a recursive solution to find the nth value of the Fibonacci series. Let's try to set n to 100 and have a look at the execution again. So one very important thing to notice is that initially the values of Fibonacci series were getting calculated fairly quickly. So if we see the first, second, third values, they were calculated in approximately no time. And as we progressed to 40s and 45s, the amount of time that it started taking to solve to find the nth value of the Fibonacci series is greatly increased. That is because the problem of overlapping subproblems is more prevalent in a case when the n is greater than the problem of overlapping subproblem when the number is lower. So when we are trying to find a lower value of the Fibonacci series, the number of subproblems are less, hence the overall time that it takes is also less. But when we set the value to a higher value, the number of subproblems increases very to a very great extent, and hence the overall time also gets very much increased. As you can see, we have still not reached to even the halfway to what we are trying to achieve. At this point of time, I would really appreciate you to pause the video for a while and try to understand the extent of inefficiency that the problem of overlapping subproblem can cause to our solution. After this, we'll try to solve this problem of inefficiency by using dynamic programming technique. So we just saw the extent of negative effect the problem of overlapping subproblems can have in our solution. So let's try to see how dynamic programming can help us in this. But before getting to know about the technique, let me tell you something which one of my friends told me a few days back. And that is, those who cannot remember the past are condemned to repeat it. This goes pretty well with the dynamic programming technique. Earlier, since we were not making an effort to remember the third value of the Fibonacci series, when the first time we calculated it, we had to calculate it again when we needed it for the second time. This is something which we can avoid by using the dynamic programming methodology, wherein we'll save the third value of the Fibonacci series when we first calculate it, and then we refer to the saved value of the Fibonacci series before recalculating it again for the second time. So the way it would go is that before we begin with the problem, we'll have an array of size 5 initialized with 1 in the first two locations. So the first element in the array will tell us the first number of the Fibonacci series, and the second element in the array will tell us the second element in the Fibonacci series. So in order to calculate the fifth value of the Fibonacci series, we need to calculate fourth and third. But first, we'll try to calculate the fourth value of the Fibonacci series. The fourth value of the Fibonacci series, we need the third value of the Fibonacci series, and for that we need the second and the first values. That can be easily achieved by referring to the second and the first values in the array. Then we add these two values to find the third value of the Fibonacci series, and this time we save the result in the array in the third location. So the third element in the array tells us the third value of the Fibonacci series. Then we look for the second value of the Fibonacci series, which is going to be the second value in the array. And then we add these two values, that is the third and the second value of the array, to find the fourth value of the Fibonacci series. So as you see again, the array is updated with the fourth value of the Fibonacci series. Now, in order to calculate the fifth value of the Fibonacci series, we need the third value of the Fibonacci series. But this time we can simply refer to the third element in the array and find the third number in the Fibonacci series. And then by adding the third and the fourth values in the array, we find the fifth value of the Fibonacci series. So as you can see the array in the top level, the fifth element is now populated with 5, which is nothing but the fifth element in the Fibonacci series. So let's try to see what this kind of an implementation where we are making use of some extra space in hoping for a benefit, uh, hoping for an improved time complexity can have in our solution. So as you can see, I have implemented a new method called Fibonacci DP, and over here I'm first checking whether the nth value of the array is available or not. If it is available, then I simply return the value, or else I calculate the value of the nth Fibonacci number, then save it in the nth location of the array, and then return it. And even passing before the first call of the this Fibonacci DP method, I instantiate a new array of size I and then initialize the first two locations with 1. So as you can see, instead of recalculating it again and again, I'm making use of some extra space in order to improve my time complexity. So if I execute this particular code, I see that I'm able to go through all the 100 numbers of the Fibonacci series in approximately 8 milliseconds, which is a huge improvement in our overall time complexity. So this is what dynamic programming technique tells us, that the first time that you calculate it, you should save the value in some sort of a data structure which you can refer to later in, and avoid recalculating. So if we compare the hierarchical representations of these two solutions, we see that the one which was using just recursion had more number of processing than the one that you can see in the right hand side. Hence, the improvement in the time complexity. Now, this type of a dynamic programming solution is also known as the top-down approach because we began by fifth and then we came down to the most fundamental problem statement wherein we looked for the first and the second elements in the Fibonacci series and then we merged them again to find the solution of the fifth number in the Fibonacci series. There's another approach which is known as the bottom-up approach. And in the bottom up approach, we make use of the most fundamental, we begin with the most fundamental uh, problem statement and then we build upon them in order to find the solution of the actual problem that is provided to us. So, in this kind of a solution, we are going to begin with an array and we are going to initialize the first two elements in the array with 1 as we had done earlier and then we'll build the solution by finding the third value of the Fibonacci series and we'll add the previous two elements in the array. Then we'll find the fourth value of the Fibonacci series by adding the second and the third elements in the Fibonacci series. And finally, we are going to find the fifth element in the Fibonacci series by adding the third and the fourth elements, which is 2 and 3, and we get 5 as a result of that. So this kind of an implementation is known as bottom-up implementation, and let's have a closer look to this. This was the top-down approach that we had seen earlier, and this one is a bottom-up approach where we begin with an array and initialize the first two elements with 1, and then we iteratively calculate all the other possible elements that will be required. That is, we are calculating the third, fourth, and finally the fifth value of the Fibonacci series over here, and then we return the last value in the array. As you see, it is not a recursive solution. This is an iterative solution. The top, the bottom-up approach is also known as the tabular approach of Fibonacci series of solving a of use Fibonacci a tabular approach of dynamic programming. So let's quickly see what is the effect does this have. So if I run this, well, again, I went through all the 100 elements, 100 Fibonacci series numbers in approximately 6 seconds, which is a very good improvement over our previous recursion-based solution. So overall, this is the gist of dynamic programming methodologies, wherein the idea is to avoid recalculation and save the previous solutions in a data structure, refer to that solution again and again as we need, and improve the overall time complexity. With this, I would conclude our discussion on dynamic programming. I really hope that you liked this discussion on dynamic programming. Please leave your comments and suggestions below. Happy coding!